we just learned how to take the derivative of exponential functions, or pretty much any exponential function you might come up with. Now, if you think to your function booklet from the beginning of the year, with the exception of natural log of x, we now know how to take the derivative of every single function that was in that booklet. Well, the ones that were differentiable. So absolute value of x is a little, I'm not sure about the derivative there. And then the other one, so some people use the floor or the ceiling function in their booklet. That one is a little tricky too, because it's has so many discontinuities. We don't usually talk about a derivative for that. You can figure it out though. But this is once we know derivatives of logarithms, we know how to take the derivatives of pretty much every function that you guys have ever heard of. There's some other functions out there, but of the ones you've heard of, we're going to know how to take all the derivatives of all those functions and all their combinations and all their compositions. So we said at the end of the last slide that once we know this derivative of an exponential function routine, we can use that to help us figure out the derivatives of logarithmic functions. So this is the process, and I'm just going to show you this process because it uses implicit differentiation. So it's a nice, reminder of implicit differentiation and how it can help us. So let's say, for example, I want to take the derivative of y, which is the natural log of x. I don't know a logarithm derivative formula yet, so I can try this. The word is exponentiate. I can exponentiate both sides of this equation. That means I can make both sides of this equation the exponent on a base of e. So it's like me coming in here and sticking a little e there. So now I have e to the y is equal to e to the natural log of x. But you'll remember that e-ing something and natural logging something undo each other. They're inverse functions. So e to the natural log of x simplifies to x. So I have this new equation that has an exponential function in it, and I actually can find the derivative using implicit differentiation. So start with this equation, e to the y equals x, and take the derivative of both sides with respect to x. So the derivative with respect to x of e to the y is e to the y times dy dx. So that's using implicit differentiation. It's the derivative of e to the y with respect to y times the derivative of y with respect to x. And the derivative of x with respect to x is just 1. So here's my new equation. E to the y times dy dx equals 1. If I want to isolate dy dx, I'm going to divide both sides by e to the y, excuse me. That's pretty easy. The math wasn't too bad there at all, right? So the only thing here is I don't want to leave a y in a function, like a derivative function, where my original variable was x. So we have seen that some functions have derivatives that involve both x and y. But that's not how we started. So I want to be able to give this derivative rule just in terms of x instead of in terms of y. So the key there is noticing that I know another way, another name for e to the y. And that comes from this statement. I know e to the y equals x, which means everywhere I see e to the y here, I'm going to get to replace it with x. So here's my derivative rule for natural log. The derivative with respect to x of natural log of x is 1 over x. That's me taking this exact same implicit differentiation work that I did, replacing e to the y with x, because I know in this case at least they're equivalent. So you're going to write that rule onto your paper, and then the chain rule version of that rule, I want to take the derivative with respect to x of natural log of u, natural log of something that's a function of x instead of just a plain x. It's going to be 1 over u times du dx. So make sure that's written in. We're going to do this example. All right, so I want to find the slope of the tangent line to y equals natural log of x squared at the place where x equals e squared. So remember, this is essentially asking me to find y prime of e squared. You can't tell me y prime of e squared until you can write me a formula for y prime. So that's my first job here. I'm going to take the derivative with respect to x of y, which is natural log of x squared. And this is not a plain old natural log of x. It's the natural log of something, a a function of x. So I'm going to have to notice that my u in this case is x squared. I can think of this as y is the natural log of u, and u in this case is x squared. So my derivative is going to be 1 over u times du dx. That's what you wrote down at the top of the paper to help you remember how to take derivatives of natural log functions. So du dx, that's the derivative of x squared, that's going to be 2x. So 1 over u times du dx simplifies to 1 over x squared times 2x, which further simplifies. Notice if you're taking the free response section, you have no obligation to simplify past there, but you might find occasions, the multiple choice test, or maybe you're going to need to find the second derivative, where it's going to make your work much easier if you simplify this expression first. So 2 over x is my derivative. You could label that y prime, or you can see here I've labeled it dy dx. They are both appropriate. Let's say y prime. So remember, this problem was asking me to name y prime of e squared. So notice, remember this notation, I can use dy dx evaluated at the place where x equals e squared. I'm simply going to take this derivative rule and replace the x with e squared. Siri tells me I should go to bed. All right, we only have one more derivative rule to learn. That's how to take the derivatives of logarithmic functions that don't have a base of e. Remember, the natural log function is a logarithm with base e. But what happens if I want to take the derivative of a logarithmic function with a different base? So I can use this expression. Derivative with respect to x of log base a of x is 1 over x. I'm going to write this a different way. This is totally correct. Feel free to write this. This is totally correct. I think it's easier to say and a little bit easier to remember if you write this. The derivative with respect to x of log base a of x is 1 over x times 1 over the natural log of a. Now, obviously, that means the same thing as what was written here, but I think it's a little bit easier to remember. I'm just basing that on calculus tests I've graded in the past. And if I want to write that same rule, but using the chain rule, the derivative with respect to x is 1 over u times 1 over the natural log of a times du dx. So feel free to use either version, the one that's printed here on the screen or this one that I've written in. They are equivalent algebraically, but you might find that they're a little easier to say. If you tried to memorize this the way it's written, I think it might be easy to accidentally forget where the natural log of a goes. So here I'm just emphasizing that both the u and the natural log of a end up in a denominator. So make sure those rules are written in. We're going to do this example. Okay, I'm going to take the derivative with respect to x of log base 5 of square root of x. So before I move the slide, tell me, what is a, what is u? Okay, move the slide. A is going to be 5, because that's the base of my logarithm. And u is the thing that was getting logarithmed, which is square root of x. So just as a side note, I'm going to need to take the derivative with respect to x of square root of x. So you know that that is, I'll write it here. So you're probably using the power rule. You're going to think of that as x to the 1/2. You're going to take the derivative is going to be 1/2 x to the negative 1/2. Totally correct. Gets full credit. At this point in your calculus life, you might like to get to the place where you just sort of remember or memorize the other version of that derivative, which is the using radicals instead of exponents version. Notice that 1/2 x to the negative 1/2 is the same as 1 over 2 times the square root of x. So you're going to see that in this next step. I think we want to just mention where that 1 over 2 square root of x comes from. Okay, so my new expression, my new plan for taking the derivative of a logarithm that doesn't have base e, it's going to be 1 over u times 1 over the natural log of a times du dx. So my u is square root of x, so here's the 1 over u. My a is 5, so I'm going to have a times 1 over the natural log of a. That's what makes that natural log of 5. And then this is my du dx. This is what we just talked about. You could write this Notice in the next line I've replaced it with the radical notation instead of the exponent notation. So 1 over square root of x times natural log of 5 times 1 over 2 square root of x. Again, you have no obligation to simplify on the free response section, but notice that the square root of x times the square root of x in your denominator multiplies together to make x. That's how I get this final answer of 1 over 2 times x times the natural log of 5. So this is a super quick summary of the 4 chain rule versions of the rules that we learned today. The derivative of e to the u, derivative of a to the u, derivative of natural log of u, and the derivative of log base a of u. And again, that log base a of u, you could write that derivative the way that's printed there, or you could use this different version if you find that more convenient, easier to memorize.